Start recording. Go live. Now we are live, and if I enable the audio, I hope it is not choppy. I have no idea why it would be choppy. No, the audio is fine now. Audio? Well, I have no one to tell me, and I hear it a bit of choppy, but I don't know if the stream is better or not. Well, I'll do it this way. So we start stream again. We did the first part of the IOVoodoo or IOVoodoo on Thursday last week. Quick summary before we start really designing the hardware. The first part, so what is the IOVoodoo or the IOVoodoo, how you call it? So yeah, the name will be IOVoodoo. Last week I wasn't sure about the name. Now it's IOVoodoo, and you can pronounce it IOVoodoo. And the purpose of the IOVoodoo is the purpose of the hardware, or the task of the hardware, is to identify input-outputs lines, or generally lines. This is a combination between these two devices. The IO finder was able to find out if a line you connect on one of the 16 channel, if it's an input or an output, and it is able to monitor it. And it's this way I can also even decode UART traffic. I created this device for hardware reverse engineering because other devices didn't work that well. So I developed my own one. And the other one, the SVG finder, is to find JTAG on board, because often when you do hardware reverse engineering, one of the first things you're looking for is the JTAG port to be able to have access to the microcontroller and do whatever you want on it. Enable root, or I don't know, just dump the firmware, and so you can decode the firmware if JTAG is not locked. As this is what the SVG finder does. SVG stands for serial wire debug and JTAG, and it's able to do both things. So JTAG uses 4 pins, SVG uses only 2 pins. It's kind of the newer version of JTAG, although it is not completely a replacement. It's just a more compact version. So the purpose of the IO finder is to combine both devices, so we can find out if one of the 16 channels you can connect is an input and output. Once we do that, we can monitor the channel for activity, we can decode UART, or we can even probe the channels for SVD or JTAG. So we decided also on the parts. This was the part. So last week I explained what these devices do, how they work, why I did them, and we decided on all the parts I will use. Almost like this. So, and you can see it on the sheet on the right here. These are the parts. Oh, this is actually the summary from last week, what it needs to do. Let's go to the summary. Through the summary, it has 16 channels, so you can connect up to 16 lines from the target port you want to reverse engineer. It's able to scan for JTAG ports and SVD ports. It's able to scan for UART ports, and it's able to test if it's an input or an output. The optional features I've added. So let's talk about the optional features. The optional features is to have high-speed serial wire debug. So for now, the scanning is pretty slow. I run it at 500 kilohertz, something like that. And it is fine enough. For scanning, it is good enough. But as soon as you want to communicate, it's a bit slower. So the idea of the device would be, first you scan, and once you scan, you can tell, okay, now be a bridge between the computer and the board, and act like a JTAG adapter or JTAG flasher. So for that, I will just have another USB profile, which I think CMSTAP offers an HID profile where you can connect to it, and then there are some standard commands to talk to the JTAG adapter. And the idea is, if I want to do that, 200 kilohertz or 500 kilohertz is a bit slow for SVD. So why not use the SPI peripherals to talk SVT, because SPI will be done in hardware. I don't have to big bang the whole protocol. And not big banging the protocol makes it a lot faster, and it's also a bit reliable. And I know that you can do SVT using the SPI peripherals. I also kind of want to do JTAG over SPI. For that, I need 2 SPI ports, because JTAG has just 2 MOSI, let's say. One of the master output slave input will be the TMS, the mode select, and the other one will be the TDO, which will be connected to the TDI of the target board. Also, why I prefer a lot master output slave input, because the term, because it clearly says this is the output of the master, the slave of the target device. Because if I tell TDO, it's probably the what I want to connect is I want to connect my pin to the TDE pin, so I cannot tell that this is a TDO pin. Yeah. What I could also do is allow, because I already have JTAG at least once, I can use the channels to do also an SPI programmer. So SPI flash, SPI programmer, SPI flash programmer, actually, to be more precise, flash programmer. And just to read-write flash programming, because I will come to that. Did I explain after level shifter? There will be level shifter, so I will be 5 volt to 1.8 volt compatible. We'll come to that later. And yeah, optional feature, if I can do flash programming, I can also identify the flash devices, because you can read the device ID or the signature, I don't know how it's called. There's the identification of flash devices, and reading that, you can figure out what kind of flash device it is. You can have a database, or you can even read extended information in the flash itself to figure out the block size, I think, and at least the flash size. Also, this is optional feature, but it will be possible, is to have an SDIO programmer, SDIO eMMC programmer. I did it only once, but it could be useful to do that, because more and more high-end boards don't use flash anymore, so the normal SPI flash, because it is a bit too slow. And for really high capacity, you always have eMMC devices, and for eMMC, you use the SDIO interface or the MMC interface, and this uses the command line. It has command line, it has a clock line, and it has a data line. Clock is always output, command and data are switchable. They can be inputs and outputs, and we need to switch between input and output also for SVDIO. SVDIO is sometimes an output and is sometimes an input. Same for data and command. I don't know. Yeah, I need command also to be an output if I want to send data. And because of that, we need, so yeah, these are the requirements, all the optional features. I think we will be able to cram the optional features, although there's no software for it. The hardware will be compatible and will be able to do it. I think so. Now, the parts we've selected in part 1 of the video, we have the STM32F401. Why did I use this one? Simply because my prototypes also use this microcontroller. Not completely this one, it uses a smaller one with only 48 pins. This is the version with 64 pins, because more pins is generally not worse, it's a bit better. And also it's the QFP package instead of just QFN package. It's a QFP package, yeah, let's say just QFP package instead of QFN, and it's a lot easier to solder. And I will have prototypes. This is I'm designing a prototype. If it has success, I can still change it, but the prototype should be easier to solder. And the QFP packages are a bit easier to solder than QFN, particularly if you don't have any stencil. Now, to select the channels, I have an analog multiplexer. It's not written in here. The shift register, level shifter. Okay, no, but the multiplexer, because I cannot. I cannot have SPI on all ports I am using. So, okay, let me explain again. To be able to test if it's an input or an output, I'm using an ADC to measure the voltage on the line, and then I put it up, I put it low, and depending on how it reacts, I know if it's an input or an output. And for that, to be able to go to all the channels, I use an analog multiplexer. This is ADC, this is the 74HC5, I think this is something like that. These are the multiplexers. And if I don't want to bit bang on all the ports, I need also to multiplex the channels we want to probe. These four channels, I want to be able to select on which of the connected channels it is, and for that I use an analog multiplexer, and that's the analog multiplexer. And actually, I have the data sheet if you want to have a look. Here, 16 channel analog multiplexer. Let's go do it this way. This is what we decided to use. I have one for the ADC, so I can test if it's an input and output, and I have 4 additional ones to be able to probe the JTAG. So we need 4 pins for SPI flash. We need a bit more actually. We need 5 of them, but I leave to the user to set and reset to the write protect, and the reset pin can be static. So it's up to the user to know what he's doing when he's reverse engineering in board, and he should be able to set if it should be able to set write protect and read protect on the board itself. So the SPI, so my IOVoodoo can cope with only these 4 signals for finding out SPI. And same for SDIO, we only need 3 pins. So yeah, we will have 4 additional multiplexers. This is this one for high performances, 4 analog multiplexers. If we do only bit banging, very slow, we have no multiplexer, but we needed to control the level shifters with direction and control output, because sometimes we want to put it in high impedance mode, so the analog multi ADC can measure actually the line without our device interfering. Level shifters. I want this board to be able to scan targets from 5 volts to 1.8 volt. More and more devices I am reversing use 1.8 volt. So very old devices use 5 volt. This is getting out of phase. Everything goes, even on microcontrollers at least, everything goes to 3.3 volt. That's just kind of now standard level. But very high-end boards with CPUs instead of just microcontroller use 1.8 volt. This is why I want to use 1.8 volt, be capable also handling 1.8 volt. And for that we use this level shifter. Here is the data sheet. That's the level shifter, 16-bit. We will have 16 channels. We will have 2 analog, 2 of this level shifter, one for connecting all the inputs, and the other one for these traces, because there will be separate lines. So we need 2 of them. I wrote about the alternative if we want to have 1 bit and controllable direction for each single bit, but we won't use it. We found out that having 2 of them is good enough, so we don't need these devices anymore. To control, because I don't have these analog multiplexers use, I'll remove this thread, set spelling up. Okay, now it's removed. So it doesn't tell if this is an error because it's not in the English dictionary. This analog multiplexers uses 4 control lines to select the channel and 1 enable disable output, so it's 5 lines. I will have 5 of them, so it's 25 pins I would need to control. Even if I have 64 pins, 25 pins just to control the analog multiplexer is too much. It uses too much. So what I'm using is these shift registers. To control the analog multiplexers, and the shift registers are serial input, serial input, parallel output. So I just stream the data to these analog multiplexers, and I will use SPI to be fast enough. I don't know how fast they go, but they are pretty fast. Here, these are the analog the shift register, serial inputs and parallel outputs. What is the speed? Okay, 100 megahertz, typical output frequency. This is the output shift out frequency. So it's also probably shift in frequency. I will never reach 100 megahertz simply because the microcontroller is not 100 megahertz, but only 80 megahertz, something like that. So this is blazing fast, and it's just have to stream the data. This is why also I will use SPI, so I can stream the data really fast, and I can select the channel in a couple of seconds, milliseconds or microseconds even. The clock, let's read the data sheet about the clock speed. That's nanovolts, volts, picofarad, volts, unit nanoseconds, that's propagation delay. I don't want to calculate. Don't you have megahertz? Yeah, here. Maximum frequency, these are the lines. Okay. So it's not completely 100 megahertz, it's 100 megahertz output, but for the input it's something around 23 megahertz. We will use 3 volts, so it's between. We can provide them with 5 volts though. If you provide with 5 volts, we can have faster output frequencies. And the inputs, let's check. If I do VCC 5 volts, I can reach 20 megahertz. Typical. This is typical. No, typical. Okay. I can provide 3 volts and it will have an output frequency of 30 megahertz. Okay. This is why they say also 100 megahertz, because at 6 volts you can go up to 100 megahertz. Super fast. Will I operate them with 5 volts or 3.3 volts? I know the analog multiplexer, I can shift in 3.3 volts, and it's good enough. This is what we see. So they will be operated, these are the analog multiplexer. They will be operated at 5 volts, so VCC will be connected at 5 volts. The idea of connecting to a 5 volt is so although I don't need it, the input's resistance goes low on resistance. So whenever you use the analog multiplexer, you have a resistance going through because it uses transistor. And the higher it goes, the higher the VCC is, the lower the resistance. This could be good. Actually, I don't need it because I can use it as input protection, and the 100 ohm inline resistance is generally a good protection. I use between 100 ohm and 220 generally for an input, 100 for an output. Either way, if I provide 5 volt or 3.3 volts, it doesn't really matter. For this device, what else does matter? That's the limitations. What we can see, a voltage input up to VCC, and typical 5 volts, we can operate with 3.3 volts. What will we do? We will operate at 5 volts or 3.3 volts. Input transition rise and fall. It is shorter the higher the voltage. So this is something which is good. We will probably provide 5 volts. And normally, even if you provide 5 volts, the input high and input low is not dependent. Here 5 volts. The inputs, if you provide 5 volts, the input high is 2.4 volts, minimum 3.1. We will have 3.3 volts. So it's fine. We can operate at 5 volts. We can operate the ADC at 5 volts, and we can even have 3.3 volt inputs for controlling the signal. Now the shift register. What if I have VCC? If I have VCC at 5 volts, the output will be 5 volts, but the inputs, will they still be recognized at 3.3 volts? What is, so the specification here, the specification high. Okay. everything which at 5 volt is the same thing. Yeah, everything which is above typically 2.4 volts is considered as high, and maximum would be 3.15 volts. We will be at 3.3 volts. So we can operate it at 5 volt and have 3.3 volt input in the shift register, and it will output 5 volts. So I don't know if I want. We can. At least I know I can. These are the main parts. Afterwards, there are plenty of other parts like voltage regulator and so on, but we don't really need. We don't really care for that. What I found out though is that lcsc.com is that last week there were still a couple of parts which were available. STM32F401RC. I don't care if it's T6 or T7. T stands for QFP and 6 or 7 stands for the operating range. You see for LCSC, they have no parts with T7, they have T6, but it's absolutely expensive, so they are absolutely taking advantage of the shortage of silicon currently, and they want to make a lot of money. You can also use other distributors which are probably less croaky, like DigiKey. They have some? No, they have none of them. I think last week they had a couple of them. Now they have none of them. Last one, Mauser. Does Mauser have a couple of them? Ooh, Mauser has a couple of them. A bit expensive, but still less expensive on order. Sorry, there's no stocks expected. I think this morning I looked at this morning. There were something like 17 left. Now there are none of them left. It's really crazy, this shortage, and yeah, expected in October. They expect to get 2,000 of them in October. That's not a lot. And T7 in September, I expect 2,000 of them. This shortage is really crazy. So almost no distributor have them. They have them for exorbitant price. So we need to buy from other shoppers' wish list, and I bought it from these guys, from AliExpress, because yeah, let's see if they come. I mean, even for AliExpress, if there's a shortage, maybe they don't have any stocks. Maybe it will come in 3 months. I don't know. It's kind of a real pain for this project. The hardware, I mean, the board will probably be first done in once I do the schematic and layout in 3 weeks. But if I have no parts in 3 weeks, the project is completely stuck, and I have to wait until September, October until new of them are. We'll see. So this is, I have no idea how big companies do. Maybe they already did their stock, and this is why everything is empty, because they don't want to halt the process. But for new devices, or if you didn't use the stock, you're really screwed, because you get no parts. We can see on Farnell. Element 14 Farnell. Oh, actually, let's use Octopart. Octopart is kind of a meta search engine. The quality is not always good on Octopart. It is a meta search engine on all devices. RC. Let's just RC. Yeah, stock. No one has stock for the T6. You see, Farnell has no stocks also. T7 also. See? What? Seriously? This is why the quality of on Octopart is so bad. Look at the picture they're using here. This is not the package which the T7 comes in. It's a QFP64. This is clearly not a QFP64, and there are plenty of mistakes like that on Octopart. I used to scrape them to find out the data, how to find out the parameters, but the quality is really bad. So I really prefer scraping Mauser or DigiKey to find information about devices or the price, because on Octopart it's completely unreliable. Disadvantage of that, I think they don't have an API, or I don't know if these have an API. So Octopad has an API, but you need a key, so you need to be registered, and you are limited if you don't want to pay a high price. But that's the business model. They make money out. I don't know. They make money out of two ways. Either they have, distributor links are sponsored. See this one, this part. It means that if you go to the distributor through their page, they get kind of back money, or at least if you buy the devices. And they sell the API access. And this is how they make their money. They make their money. Profiling. So they have an API. I don't know if DigiKey or Mauser has an API, but I just do web scraping. I go on the link and I scrape, for example, if I have this part number, I scrape this page and I just extract from the table all the information. And this is how I populate my BOM, bill of material. But other tangent, we are not that far for now. What we know is that no one has this part anymore. I've ordered some of the chips on AliExpress. Let's see if they will get shipped. For now, they didn't get shipped. If they don't get shipped, then I have to find something else. I mean, I do have boards with the CC model, so I could desolder the CC model and solder in on the new board, because I'm sure the CC model is also not available. Let's see. CC, that's the QFN package. Yeah, see, completely empty, all the stocks. Oh, I don't know what epsilon. What is epsilon? This is not QFP, it's BGA. What is the epsilon? Ah, yeah, sorry. Chip level, wafer level, chip scale package, chip surface package. I don't remember what exactly what it is, but it is almost a bare die. They have a couple of them. Actually, the CC epsilon, how many pins? Yeah, 49 pins. I want 64 pins. I want to do the design with 64. I can change the package, but I still want the 64 pins version. No one has that. What you can also do, can you order from ST? I've never ordered. I'm sure their stock is low. Can you order from them? They have a shopping cart, so why not? Shop, eStore, same with scripts. STM32F401. Can we get from the supplier? RC T6 or T7? Yeah, don't care. They have the price. The price are not expensive. Do they have in stock parts? So these are the development boards. I really recommend the development boards. They're well made. And I'm not using them because they're not small. They're really for huge package development boards. They include so if you want to use the infrastructure, the development board, I always recommend the development boards for manufacturer, because it's a proven design. It has really good documentation. You can have the schematics, you can have support. If you use the ID, it's quite good. I'm using these development boards because they're really inexpensive, and I know what the faults are, and I don't want to spend $50 every time I do a prototype of a project. So in quantity, yeah, $5. Maybe I'll order from ST. They don't have a lot in quantity anymore. RCT6 1 to 10. I might order before the stock is empty. Yeah, out of stock. Out of stock. Out of stock. 77. I'm sure in a couple of hours it's not there anymore. What is the shipping costs? I'll do that after the stream. Still hoping, and after the stream there will be some of them still available. Actually, let's add five of them. Add free sample. Okay. that could be good. I'm only doing a prototype, so a free sample, why not? Free sample times quantity. How much can I do? Had 2 updates? Still a free sample with 2 quantities? I don't want to abuse the sampling part. I want to make a prototype. Estimated shipping, sign in and checkout. I've never ordered an ST on ST itself. I did order from TI, so I have a TI account. I don't have any ST account. Estimated shipping. I don't want to dox myself, but I need to do it. So I will order it. So you don't see the order and you don't see my credentials and so on, blah blah blah. I will switch off the stream for now. I will switch back on. Just wait for 2 or 3 minutes, and I'll be back. Let's try to order before all the parts are not available anymore. So see you in 5 minutes. And we are back. So I created an account and I wanted to buy it. And although it says they have 77 in stock, well, you cannot buy them. Whenever you go to checkout, you see that 0 quantities available for immediate shipping. So they have 17 stock, but none of them in available shipping. And it doesn't matter how many of them I'm buying, and if I pay for it or if I want just a sample, it doesn't make a difference. I cannot buy them. So even from ST, you cannot buy any chips anymore. So I'm really wondering why they are offering it. Maybe you have to contact sales and they can unlock for your account, some things like that. I don't know. Um, but yes, I cannot buy even these parts from, well, any of these parts from ST. So really the last place I have is either paying a horrendous expensive price on LCSC or pay a decent price from AliExpress and wait until it arrives and hope it arrives. But I'll have to do that. And yeah, we spent 45 minutes. No, not just for that. I explained. I had an introduction about the hardware design. Now we can finally state the hardware design. So this is not an issue for me anymore. I will take care of the other. I just hope that the other parts are available. So microcontroller, I think it's the hardest part for now. But maybe the other parts will be available. Let's check, for example, if we look for this device, I'm sure there are still some of them available. Yeah, there are a couple of them available, not a lot, but there are still, yeah, for example, this one, SUP is a bit large, but I don't care because they will be next to the, so quantity available. Can I check is in stock? No, I cannot here tick in stock. 4 cents. Okay, they don't have a lot of in stock, but for 4 cents, it's pretty amazing. At 30 cents, it really depends. This one is 50 cents, 4 cents. What about the data sheet? 3.3 volt, 5 volt, Fmax 25 frequency, SOP is a bit smaller. SOP, generally SOIC is has a pitch of 1.72 millimeters or 500 mils, no, 50 mils. And SOP has a pitch of 1 millimeter or something with millimeters, not imperially based, but we can check what the pitch is. Pitch is often small e. Oh, it is a SOIC actually, and not a SOP. SOIC is just one of the packages from, so SOIC can be a SOP package. Don't know why. We'll come to packages though. We'll come to packages because we will have to design the parts. So yeah, they seem to. So these shift registers are really existing since a long time. There are only a couple of transistors. There's nothing which is really really hard about them. This is why I'm not that surprised that you can find them for 4 cents. And since we will talk 3.3 volts or 5 volts, we can use any of them. I don't think it will make a difference. They all have. We have to check this. This is for sure. We have to check the pin out if it's pin compatible. But most of them are pin compatible because they want you to be. They want you to buy from them as an alternative without changing the package or without changing your layout. You just swap the parts. Here it says SOIC. And yeah, this is looking at the device. This is also a SOIC device. Well, there are still a couple of them. Now the level shifters. Let's check for the level shifters. So this is the. Let's also check for the analog multiplexer. Don't remember which the difference between HC and HCT is. We've looked at it the last time, but I think it's not relevant for us. HC, yes, there are some in stock. We want, yeah, why not? I do have some in stock already. Yeah, I do have some in stock, so I don't need to buy any of them. And actually have something like this in stock. So I don't need to buy these ones. The level shifter I need to buy though. And we looked at the last time, we do need to buy the one from NXP and not from TI, because the one from NXP, there are plenty of them in stock. The one from NXP are 1.8 compatible, the one from TI are not. T-sub 48, this is T-sub 48. What's the difference between both? DG11, another kind of package. We'll check later on. But the price has gone up. I think it wasn't that expensive. I need to track them. I need to kind of encrypt the track. That would be nice. I will create, because I already have script to scrape LCSC, DigiKey, and I think also Mauser. I had for Farnell, I had for Octopad, but I don't use these services anymore. I will put my most common parts, and I will track the rising and lowering on the prices. So for resistors, it doesn't make any sense. They're always cheap. But something like ICs, I will have a couple of microcontrollers in the list. Every day I will grab the prices, and we can see the shifting prices during time. And I'll probably also add a couple of these ones. Because yeah, the script can run. I mean, it checks 1 time a day or 2 times a day. We will do this, and next time, this is yet another project we don't want to do right now. What we want to do right now is designing, and after 1 hour I will start designing the hardware for the IO finder. So we have the parts. Now that we have the parts, we can kind of draw the schematics, but this will not be the case because I don't have I do have parts. That's my part list. Yeah, hardware, I started it, and this is my library of parts. I make my own library of all the parts all the time. I do not trust the libraries of other people. I've run two. The problem is, whenever you use the library of other, it might work, it might not work. You don't know the quality. If it doesn't work, it's really a pain because you blame yourself for using someone else. If you create your own library, you can do checks and you can really ensure that it works quite well because you tested it at least once, and or you created it yourself, so you can have insurance. And if you did something wrong, then you know you did it yourself, and you can have a checklist to say, okay, next time when you create a footprint or when you create a symbol, do that. And sometimes you just don't find symbols. There are plenty of ways to download symbols. I don't download the symbol from someone else I don't trust. First, because I don't know if the path is right. If all the device, the analog device, and second of all, if I do it myself, I can really customize how I want it. For example, if I want all the VCC on top, or if I want all the VCC as a separate part, I can do that very easily. If it's downloaded, you have to use whatever you want. I don't know. There are plenty of libraries now which give you schematic and so on, and you can even download them. I think plenty of them do them now. You can even download the schematic, so I could download the schematic from the manufacturer himself. But maybe I don't like the format. For example, this is even more important for footprints, because on footprints, how do you mark pin 1? Do you have a point? Do you have a triangle? Do you have a corner? Do you have a 1? This is something that you cannot control. There are footprint generators and so on. So I make parts. I make all the parts myself. For the microcontroller, I do have the 401. I made it last week, but I don't have all the other parts, so we need to make all the other parts, and I will show you how to do that. It will take a lot of time, and then probably take the whole stream. I will make just parts and find out if it works or not, and we will not even be able to start the schematic, but at least I have a library of parts. I have plenty of parts which I already use for general things. So I have the multiplexer. This is already inside here. This thing is actually not the device itself. It is a description of the device. Let me show you. Data project IOVoodoo hardware. This can go. This can go. hardware. So let's write current task, create library, parts library, parts library. Vim library. Is it big enough? Let me just increase the font for you to be able to read it also on the stream. That should be plenty enough. IC, and we will have the multiplexer. So this .yaml is a file format for how you represent text using tabs and so on. It is, I think it's called yet another markup language. There are plenty of markup languages. This is one of them. This is how it looks like, and actually I use YAML because this is how you describe a part for a software called Kida. Not sure how you pronounce it. I'll show what it is. GitHub Kida. Okay, I didn't write GitHub. Kida. This is a footprint generator. I'm using the old one, so there will be a new one written in Rust. The old one, this one, is written in CoffeeScript, which is kind of a derivative, one add-on for JavaScript. It's very JavaScript. And this part's Node.js library, exactly. This part allow you to generate footprints. I had my own footprint generator. I find this one quite good actually. I even contributed to it. And you describe your device using there's even dimensions from NXP. So you describe using YAML, and then you let it generate. So is there an example footprint layout? Yeah, example. This is using YAML, and then once you have YAML, it generates two things out of it. It generates the schematic symbol, because you give the property, and then you can say how the schematic symbol is supposed to do, and it generates the footprint. And this is probably the most important part. So if I had a footprint generator, it only generated footprints. It didn't generate the schematic symbol. This does very good footprint generation. Also, according to, I think it's written here, IPC 7351. Is it this one? It's probably not in here. 735. Oh wow, I still remember it. IPC 7351. This standard kind of defines, according to a package, it kind of defines what the land pattern is, and the land pattern being the footprint. So they call it land pattern. Footprint could be actually just how the leads are. So here defines how the leads are. This specification tells you how to calculate the leads. I have it, and I can show you what the specification is. Data, electronics, IPC. And this one, yeah. So several ways to do it. What is important is whenever you have, so this is, for example, the package outline. It really defines the dimension of the package, the pitch, but also the size of the leads and so on. Afterwards, I think in the same schematic, in the same datasheet, no, NXP doesn't do that. Some recommend a footprint layout, a footprint or a land pattern, whatever you want to call it. Package outline, this is this, and okay, they don't provide, in this case, they don't provide you the recommended land pattern, but there are plenty of other datasheets which do that. And probably, let me find a datasheet which actually does that. Maybe I have one. DST part probably does it. Datasheet, that's the datasheet of the ST parts. Let's look at package information. This is the package information. Do they have a footprint recommendation? Here. Oh, this is the footprint recommendation. Yes. So this is the package. These are the dimensions of the package information, and the manufacturers gives you a footprint recommendation. So these are the size of the pads on the PCB and the drawing on the PCB on the LAN pattern. Now, what IPC does, the IPC 7351 date specification, which I had open but don't have anymore, it's this one. What this one does is, looking at a package, I will tell you how to generate. So here, looking at the package, I will tell you how to generate the footprint for it with tolerances and so on. And you can have 3 tolerances. Here, you see all the tolerances. It tells you how you calculate it and so on. And it has a couple for a lot of packages. There are always 3 density level A, B, and C, which they call maximum, medium, no, most, nominal, and least. Most is really for clumsy hand soldering or for really robust things like, I don't know, military or space. Nominal is that it's what you want to use most often. It is still solderable by hand. Least is very tiny. It is only meant for machines or very small parts. These always define you what the dimensions are, what the round-off factor is, and it tells you, corresponding to a flat ribbon lead package, how you draw the LAN pattern. So it is good because it's a generic way to generate a LAN pattern according to packages. So what you always have the choice to use the recommended LAN pattern from the manufacturer, or you generate their own one, or you draw their own one, as you want. And this is good because the one which has, for example, if we look at this one, here we have only one LAN pattern. It doesn't tell you if it's recommended for hand soldering, for a really robust design, where you have larger patterns, or for really miniaturist thing. It's only one LAN pattern. IPC allows you to select between several LAN patterns by defining which density level you are using. This is already one advantage which you can set, which these data sheet don't offer. So most of the time this works, but if you want to be IPC, if you want to have always use the same rules, you can use IPC rules. And this Kida software, which is here, generates the patterns according to the IPC. So what you do see, you describe the part using the YAML, and we see, okay, the housing. The part is not described in this case, but I did describe in my case. Did I? No, I didn't, because another thing which is important, you have the package, for example, sub QFN and so on. The package, for example, here it's QFN, and then there is UFQ QFN. This also tells you how thick it is, what the pitch is, and so on. This tells you the package. So there are plenty of ways to have. So the package doesn't really define you QFPN. QFPN is a mix between QFN and QFP. Okay. So this really doesn't. Just the package doesn't tell you the dimensions. But what you sometimes see is that there are standards for packages actually, which are defined in JDEC, and this is what you see here. So JDEC, I think there are a couple of institutes which defines them. For example, JDEC, but there are other ones. I think this one, JAEC, this is the American version. I think JDEC is the American version, JDEC European, I don't know. And NXP does his own one. But for example, JDEC gives you a couple of standards what the dimensions of the package are, and this includes everything, the leads and so on. So we can remove this, and I'll show you just one JDEC part. For example, something like this. Not at all like this. This is component front area. Okay, let's do another part here. Something like this. Something like this. So it is pretty old, you see, because it is scanned from other standards, but I think you can download most of them for free. And here you have the dimensions in millimeter, and if you look, you always see that if you comply to this JDEC, this is the code number here, MO152. If you comply to MO152, you will use these dimensions. You have this lead pitch, you have these tolerances. So there are kind of classifications of sub. So this is a sub part, but in the sub part it uses this really outline, this category of outline. And sometimes manufacturer will tell you which they use. So here, for example, they tell it's a sub 16. I think TS is sin. I don't know. This tells about the height. They gave you the units, but also what you see here, the references. They have the outline version. This is the internal parts. This is the internal part number for the outline. They also have a JDEC alternative, and they say we comply to this JDEC using all the dimensions and of tolerances. Now, KEDA, I don't know how to pronounce it, has a couple of JDEC already implemented. So what I did for this part is I just had to say this part uses the JDEC specification MS013. AD is actually for the number of pins, and there are a couple of variants within these. That's here. There is this one here. So this is SSOP, and then there are a couple of variances. This one, lead pitch, body width. Here exactly, variation. You can see the variation here. If you have 8 pins, it's called AA. If you have a body width of 4, a lead pitch of this, and a lead count of 8, then the variation is called AA. This is what you see here. So you specify which JDEC specification it is to, and then the variation. And just using that, I can generate a footprint because I know the exact package, and it will. So this is the housing, and because the housing is defined, it will be able to do that. Now, not all manufacturers do that. For example, let's use the run from ST, and we have a LQFP, so QFP 64. Here we have some outlines. Maybe it complies to a JDEC, I don't know. It is not written that it complies to any JDEC. Are there? No. But at least they provide all the dimensions. And if you don't want, if it doesn't comply to one JDEC, maybe it does, maybe it doesn't, but at least you have the things, you can implement it, you can define it yourself. Library, MCU, STM32F41. Here. This is what I did last week for one of them. So you define the pinout for the different packages. What pin is on what position. For example, PB0 is on pin 26. And then if I go to the end, I can see that the housing for LQFP will be only interested in LQFP 64. We can define the pattern, and then we can define all the parts. And actually, if you use like this, if you have JDEC just does exactly that. There is a template which defines the body width, the body length, the height, the lead width, and so on. If you don't have an already predefined, you can write it yourself. And based on that, KEDA will be able to generate the land pattern or the footprint. You can have a bit several options. This is how I generate my symbols and my my land pattern. So they all are generated the kind of the same way. They all respect the same things, because sometimes when you download, for example, if you, so it's not written here, for pin 1 indication, you could have a seal screen marking the end of the fabrication zone all around the IC. Most often it's done for chips, for chip resistors. you have, like, for example, like this camera. Try to make focus here on this package for the diode. Here you have a silk screen around the LAN pattern telling you actually which one is pin 1, but this one doesn't. Actually telling you where you should put the path. Sometimes, if you download it from just any website, you don't know, will they add this seal screen? What will be the width of the seal screen? What will it indicate? Will it indicate the courtyard? The courtyard meaning you are not allowed to put any parts within the seal screen, because this is what is used for the tolerances for the pick and place machine, or because it has hangouts and things like that. And all of that you can, if you download it from the wild, from any kind of source, you don't know, do they respect this kind of design rules? If you generate your own footprints, then you just set up the rules and it does everything the same. This is why I do generate the footprint. So it's, in the end, when you have a layout, you have all the parts which respect this kind of design things, and it's a lot, it's proper, and you don't have a mix of plenty of design rules of different designs. So we do have already one part, and we'll do it for the other parts actually. We do have one part, we do set spelling, okay. So it now, there's still syntax highlighting because it it's a YAML, so it can syntax highlight. And we have the part for the multiplexer. This is this one. Did I put the data sheet? I put the one from TI. So let's see if the one from NXP has the same recommendation for the layout. This is the data sheet. That's the housing. So this is the kind of symbol, and then somewhere we have, where are the packages? Package outline. Here, package outline. This tells that the package outline in SO24 is MS013. Do we have, so it seems TE does it, MS013 for SO24. I think SO24 will probably be the SOIC part. For example, for this, we can actually check for SUP, SSOP24, MO050. Do we have MO050? MO050. Again, here they don't tell you which variation it uses, so you have to look in the MO050, the one for 24 pins, and they're generally just one variation, or you look at the body width, for example, 050, MO050. This is MO050. Here are the variations. Variation nominal, variation D. The pin count here. Pin count. You see pin count 24. There's only one variation, AG. And is this what we have in a data sheet, in a specification? Yes, AG. Whoop, sorry for the POC. I just landed on my microphone. So we have two parts. We have the one from, this is from TI, but it seems to be pretty psych SKU. Oh, this is what I added myself, how to order it. And I think I've ordered, this is the stock I have. DigiKey, this is the other things. This is also where I add my my information. So I think it is not passed by KEDA, but I still add it in my path, so whenever I open it, I know where I can order it from. So I did this from TI, probably because the one I ordered was from TI, either from AliExpress or from DigiKey, but it seems that the same apply for the NXP part. And I do have in stock the one from the NXP, from TI. So this is the footprint I have. I've tested it once, it works. Actually, did I? No, I didn't. I didn't finish the design for this thing. No, I didn't. Which use this part. This is why I still have 20 of them in stock. Now we do it for all the other parts. It's already done for resistors, LED. I think I already have it for fuses. We'll see afterwards. What I did it for, so we have the multiplexer, we have the microcontroller. What I don't have is, so I can remove this. What I don't have is the shift register. This is a part I've never worked with. And the level shifter, I did work with level shifters, but I didn't work with this one particularly. This is the multiplexer, we don't need it anymore. This is the outline, we don't need it. Try to keep the desk a bit clean. So let's make a file for this part. I'll add it to the other screen. So I always have it in parallel, so you won't be able to see it. Can I tell? Yeah, I can put it in this screen. 3. How can no? There was a way to. No, that's okay. This was the way. Okay. Up. And now you can also see the data sheet on the right hand side. Let's start creating the footprints. Lib library IC IO expander. No. How do we call it? Level shifter or voltage shifter or voltage translator? Level shifter. Translating. Oh wow. NXP calls it translating transceiver. Plenty of names. We will call it level shifter. Level shifter. NXP. I write everything small. I don't remember why, but I do write everything small. I think it's better for the software. ILLV 164245 .yaml, and I always have to see what the description is because I don't do very often my parts. So level shifter NXP 74 ALVC. Yep. But we can copy because we can copy the information from the other ones. Name, copy paste. This can be in caps. Variations. There are 2 variations for this part, the SSOP and the TSSOP. TSSOP, I think T stands for thin, so it is not that high. We don't care about the height in our case. Description, we will copy it from the database, from the data sheet. Up. Voltage translating receiver. We will put a link to the data sheets. Analog. This is not an analog multiplexer, digital. Level shifter. Let's say put it this way. I don't really care. Up. Let's find the data sheets. The link to the data sheets from NXP itself. Here. Diode. Not the diode. Nah, that's a link at least. So the link goes here. Now we have to describe the pins. This is what is here, the pinout, sorry. And we can actually group them, which is quite useful for later on. Pinouts, I think you can have tabs, but I'll have this. For that we will use the function diagram or here, pin description. we have gear. This is the direction control. Gear 1 gear it's called. Okay. Can we start with a 1? I don't know. At 1 gear it's pin 1. Nope. 2 gear is pin 24. This is what you see on the side right there. Oh, the white on black is not really useful. Wow. You cannot see it really well because the transparency of this thing is far too high. Can I change the transparency? Filters, transparency, 80%. Let's put it to 90%. Okay, close. It's a bit better. It's not perfect, but it's still readable. Else you just open the data sheet and you'll find it. Probably you don't even care. Then we have input output. Why do we say output? It is bidirectional. There's a side and a B side, and there are 2 of them. Let's call this one 1B. We have 1B0. 1B is a group. It is divided, so it is 16-bit translating devices, but it's 2 group of 8. This is why we have this 2, and I'll just fix it this way. 2, 3, 4, 5, 6, 7. The pins are 2, 3, 5, 6, 8, 9, 11, 12. Then we have 2B, so we can copy this. 2B. Uh, 13, 14, 16, 17, 19, 20, 22, 23. We have the same for A. Actually, we should, to be logical, we could have, we will fix that. We should have A first and B afterwards. Let's first do this with the pins. So 1A, 47, 46, 44, 43, 41, 40, 38, 37, 2A, 36, 35, 33, 32, 30, 29, 7, 26. Because it sounds better to have A before B, we will put A before B. Direction. We put it a bit lower because these are control lines. Then we have output enable. We have 2 of them for 1 and 2. Actually, it's called 1AO. I think there is a way to negate it, to have something of a negation, so you indicate that it is active low. I don't remember how this is done. It's been a while. To output enable 25. Then we have power, or let's call VCC. VCC, there is VCCA and VCCB. VCCA is 30. There are two VCCA. Why? Maybe because it's 1 and 2. That's weird. I don't know if you need. Do you need capacitors on both of them? We'll have to look in the datasheet. VCCB about decoupling capacitors. How? I hope there is a design recommendation. Generally, I put, whenever there's a VCC line, I put 100 nanofarads capacitor just for decoupling, and I don't ask too many questions, but sometimes, for example, they require more. So we'll have a look at the datasheet. VCCB is on 7 and 18. Then we have ground, and how many grounds? Wow, plenty of grounds. Okay, grounds, wait, 4, 10, 15, 21. Maybe they're all interconnected and you don't need to connect them all. That's quite possible, and you can use them as bridge. This has to be read. Sometimes it's not written in the datasheet if it's interconnected or not, if you need to connect all of them or just one of them, and then can use the other ones as kind of a bridge from one side of the part to the other side of the part, so you can create ground islands. I don't know. Let's check if there's a recommended design. Package, League of A. Recommendation, no, that's the recommended. Static characteristic, package data abbreviation, legal history, functional diagram, nah. No. Input capacitance, that's not what we're looking for. Input output capacitance, power dissipation capacitance, output capacitance. What is this? Test tier kit. Ah, here. What did they use? Oh, but that's just for testing. This is VCC. They didn't tell what capacitance they put on VCC, just on the probes. Nope, they don't tell. So I will still put 100 nanofarads. On here, there's no recommended design. Is there? Design. I got information. Disclaimer. Blah blah blah. Nope, there is no recommended design. Maybe there is somewhere written, but I didn't see it while looking at it. So we have all the parts for the footprint. Pin description. We have direction and BB key ground output enabled. Yeah, pinout is done. After the pinout, we have to define the properties. Right here, the properties of parts. This allows, when you generate the schematic, to have some kind of information. We have bidirectional. We have 1A, 2A, 1B, 2A, 1B, 2B. These are bidirectional. Inputs, everything which is steer and output enable, are directions. And I think this is where you put inverted. I don't remember. Power is VCC. Yes, ground is ground. This is done. There was some way to have some kind of, did I write it here, where some input is negated? For example, here n reset is negated, and the property is inverted. Yep, that's how you say that something is inverted. Inverted output enable. These are the properties for all the paths independent of the package. There are multiple packages. Did we put the multiple packages yet? This is called the variations. Is in the variation and the ordering information. How do you know which packet is package outline? Okay. You see that XP has its own one, SOT, and it often complies also with the JDEC one. And this way you can create a database of templates from parts. Ordering information. Here. The suffix. This is the suffix which they use for SSOP. This is the suffix they use for DGG. Keda, do you claim to have some of the NXP parts? It could be nice because it's an NXP part to actually use the NXP part description. Else we use the JDEC one, but just out of curiosity, do you have them? Source, pattern, common. Wow, it is a psych coffee. This is general psych. Okay, where are the patterns? I don't recommend. I think they're generated. It's been a time. Been a couple symbols. No, not symbols. Source, pattern. I did write some of the patterns, so I know they exist. Calculate. Can search for it. For example, MS or JDEC. Just look for JDEC in this repository. Yes, JDEC outline. So these are outline here. Share outline. This is where they are. Outline here. NXP. They do have only one, but they do have them. SOT 28, and you can see this is how the template looks like. Oh, SODF. I don't know what. SOD. Okay. Option polarize. This is how you describe the template for package. And we could, if we want, we could add this. We could add our own for this part. But there are also JDEC ones. Maybe the JDEC ones are already there. JDEC. You see JDEC. There are a couple more. They're not all of them. So it's just there are not a lot of people actually using this software. Probably the creator himself and me, maybe. Oh no, there are 10 folks. So if there are 10 folks, there are at least there are 10 members. Some users, at least 10 people are using it. Ooh, lot of people. Let's look. So these are the variations. Let's look. Let's make this. This we don't care. That's the STM. We finished it. How does the schematic? We might have to define the schematic symbol. I didn't order the parts now, so I don't put the SKU. Yep. Symbol IC. Yeah, we will use it as IC. On the left side, we will have schematic again. That's the schematic symbol. How do you do the schematic symbol? This is really up to you. Generally, I have power on top, ground on bottom. On the left side, input. On the right side, output. So what we will do is, like we have this function diagram, we will have something like this. On the left side we have the A part and the direction. On the right side we have kind of the output, which is the B part, and the output enable. And actually we will have to rotate it because we will see what A part is and B part means. So on the left we will have the direction 1A, 2A. On top we will have VCC in ground, and on the right part, and it's 1A, we will have the output enable 1B and 2B. Nah. 1B and 2B. This will be the schematic. We will generate it afterwards, so we'll verify if it looks well or not. SKU, we don't care. Housing. Housing, there is SSOP. The suffix for SSOP, at least for the NXP parts, because every manufacturer do their own suffix. For the SSOP 24, it's DL. And the outline, let's do it for both, so I don't have to switch pages all the time. For TSSOP, it's DGG, that's the suffix for this part. Now let's have a look at the packages. Package outline. This is for SSOP, we have MO118. JDEC MO118 is MO118 existing. MO1, no. It's not. So I have to create it. So I have to download it. Okay. And then I have to push it to the repo. It's always a pain to make parts and to make your library. It takes as long as creating the schematic as making schematic conventions, but really one part which is important. It's not important when you start schematic design. You just use the parts which you find and libraries which you find. You don't want to dwell into creating your own symbols because it can be really complicated and you don't know all the subtleties until you do a lot of electronics. And there are probably a lot of subtleties I still don't know, but I know the pain of footprints. And afterwards, you just spend hours and hours on footprints and on parts, on libraries. In companies, you have dedicated people which only do that. They only do parts and libraries all the time. And in this case, for example, I do have a repository with all my parts, which I upload, and for each project, I have my own version for each project. It doesn't have to be common. Sometimes I do some tweaks because I want another representation, or I want some other guidelines, and so on. So every of my project using its own version. Often it's the same as the common part and in my repository, but it doesn't have to. It allows me to tweak the things. So we don't have this JDEC parts, this MO118. So let's download it from JDEC. JDEC MO. Now I show you how it works. JDEC MO118. Oh, this is fun. The JDEC, if I did put 118, it actually ports on the asset from, and is it the same? SUT 370, SUT 371. Yes, 371. That's the same asset than the NXP. So we could actually do this instead of the JDEC one, because it's often the same. We will do both of them. So in the repository, there will be both of them. They will be very similar. So that's the JDEC part, the NXP part. Is this the one from? Oh no, this is the list. So this is the lists, and we want to download them. I don't remember where all the files are. Copy, link, address, files. Okay. JDEC MO118 search. This one. But to download it, we need to log in. And to log in, I do have a fake account. I think it's even a shared account. We don't really care. Yeah, now we can download the thing. This is the package. Quality is not as good as the one from NXP, but yeah, it really defines the package, or it even defines the footprint, but we don't care about the footprint. And there are a couple of variations. Yeah, you see again the variation corresponds to the number of pins, 48, 56, and so on. We will do both of them. We will do the JDEC one and the NXP one. Which one do we want to start with? Do I have a checkout actually? I think I do. Let me check. Somewhere where you cannot watch what I'm doing and you cannot watch my secrets projects. Is it useful? Keda library, no, this is my library, but it's not Keda itself. I have to check it out again. I do have our own repo, so I did fork it, so I could use this. Yeah, we will do it for this part. So you see, that's the project. And whenever you want to add some to contribute to the project, what you do? Oh, there's a pull request. Okay, that's a bit too old. Whenever you want to on GitHub submit something, you either create an issue, but that's not the right way to do it, or you fork it. There are 10 forks. One of them is mine. IOVoodoo, that's me. And we can use this branch is there a commits. Ooh. We will download this one. I am behind. Don't know what the a commits are. And I created some pull requests there. You see, every one of my branches is actually. Oh, you see, I did submit already some JDEC footprints. These are the branches which I then put to Keda using pull request, and we will do exactly the same. Let's open again. It will be on the left side. Data project IOVoodoo git clone. How does it work? I don't remember. Just SSH, this one, and then it recognizes my account. I could log in. Oh, it does. I never remember how you sync with upstream. I always have to look this. I don't like GitHub. I don't. Git is super powerful and super complicated. Git sync with upstream. Thinking of fork, exactly. GitHub. How do you think of git fetch upstream? We have to add the upstream first. Upstream does not appear to be a Git repository. Configure a point that is upstream repository. Yeah. We have, this is our own thing, exactly. Now git add upstream, and the upstream is the official Keda. It's this one. This is the upstream. Is there something else to do? Git remote? No, we can still check. Yeah, now we have the upstream. For the upstream, we don't have an SSA access. We don't really need to have an SSA access. Actually, I don't remember if the kiddo did add me as one who can push directly. How do you see the members? Don't remember. Contributors? Okay. So I'm not one of the contributor, meaning I have to open a pull request, which is completely fine by me. So I cannot push directly to the repository. Fine. I just open a pull request. So this is this. Now syncing a fork. Git fetch upstream. Okay, master, new branch, upstream master. Yes. Git checkout main? No, master. Already on master, okay. Git merge. What do they call main? No one uses main as a name for the master branch. There's a kind of a joke. Whenever I use a branch on Git, it's master. Meaning you don't create any branches. There will be a fast forward. Exactly. Fast forward. Oh, actually, these are. So it's just that my repository has not been. This is from me. I remember having worked on these things. So the fast forward is just that my part wasn't updated. So now if I did git push, I should push master to be in sync with Keda. Is it the case? So this is mine now. F5. Yes, is even. Now it is even. Now we can fork. We will start with the MO1. Git branch. There's a command to branch and check out at the same time. I will never remember what the command is. Branch MO. It's not too important because it's just git checkout MO. Now we are on the checkouts. Now we can create the parts, and I will copy the closest one because they are very similar. Share, outline, JDEC, and then we will modify it. MO, we have 118. What is the closest? We can have a list of the things. 179. Let's use this one. The issue when you copy is that you not create new ones, so you have to be really aware. You have to pay really up attention that you don't reuse too many things. Actually, we'll try. Let's see. Now, yeah. Tab edit. We are in library here, aren't we? Maybe not. Keda. Okay, yeah. Keda, share, JDEC, outline, sorry. JDEC, MO11 and only one. Pattern sub. So now let's have yes. Oh, I didn't write this. I don't know what this stands for. This is an escape sequence. What is the escape sequence V? Or is it an escape sequence? Now I'm interested to know what this feature is. MO137. Do I have MO137 in my parts? Doc. Electronics JDEC MO. Oh, I don't have a lot of MO. 137. I don't have it. We have to download it. JDEC. Yeah. Dismiss. Login standards. MO137. 137. That's a sub also downloaded version E. So in the end, oh, I see. This has been renewed a bit. It is still crap. It is not selectable. I don't know how they do their export. Here you see that the administrator which created my documents have properties. JDEC standards, that's the meeting, 2010, okay. It's quite new though. And I don't know, they use this to create it, and Acrobat Distiller has apparently issues to export text, which makes it selectable. Kind of a pain. So what is 1V? AV here, A. What we saw here is AA. So these are the variation table we have. What are the variation tables? Actually, they're not the same variation table. Variation table. Here, AA. I have no idea what AV is. IVD? I don't know what this thing is. Something about I don't know about Keda, which is fine. But I don't figure it out really fast. These are the variation. Why is this variation not here? This is nice. This is an escape sequence for Word. It's not an escape sequence like Newline or something like that. This is a pattern escape sequence, meaning that this is nice, and we'll use that actually. So you see that the A height is the height. Which part is height? Height is A. That's the letter A. It's height of the body or height of the complete thing. I generally like to put where this comes from, where this number comes from, but this is the height, and we see that the height A is 0.069. This is all in millimeters. JDEC does everything in millimeters. What we see here, and this is common to all variations, all A variation. It is different for the B variation, and this is how it tells him. Everything which starts with E and there is another word, so AA, AB, AC, use the same height. The more I look at Keda, the more I like it. There is a newer version, or there's a rewrite actually in Rust, but it's not complete. It's still work in progress, but the one for using JavaScript, CoffeeScript, or Node, whatever you want to call it, it is slow, but you don't generate the footprints every day or every minute. So even if it's slow, it works perfectly fine. That's nice. So we want this one. This one is let's leave it open. From when is this one? June 93. This is the last time it has been changed. Since then it hasn't been changed, and because this is also a sub package here, SSOP, shrink small outline package. It's very similar to this one, plastic shrink small outline package. So this is PSSOP. I don't know if this is not plastic, what it is, but who cares? It's the same basis, so the numbers should be very often the same. variation. And the variation is this a D? C variation, yeah. So it's the same for all AA. That's really useful. So body width. And the body width is the E1, I think. And we will check if it's really E1. Here we have E1. If we look at E1, E1, 154. This is 154. So very often, so what you often do is you have tolerances on packages, on everything. This is why also kind of the IPC is good, because it includes tolerances, which is kind of important. You have the nominal, maximum, minimum, and depending on that, the footprints are a bit different. Sometimes it is written, so min, nominal, max. Sometimes it's just JDEC, it's just this value, which is kind of the nominal value, and then there's written BSC. BSC is defined somewhere as being plus minus something. I cannot do Control F to find where BSC is defined. Here, DBSC. And I think these are the variations. Yeah, these are the I don't remember. I don't know what BSC stands for. These are the variations for the D value. We want the variation for the E value, or actually the E1 value. Where is BSC documented? And so very often you find things like that. Here it is often described what everything is. And you see notes. What is BSC? Reference, issue, position, notes, issue D. Where is BSC defined? I don't do that very often. We could also put just a nominal value, but we want to do it properly and put the BSC tolerances in form. Why is it not in the tolerances? I thought it would be. Here we have ref tolerance, which is kind of weird. I don't know what this means. Ref. I don't know what ref means. Ref. I don't know what this means. Reference to what? Don't know. Dimensions and tolerancing as maybe the tolerances are defined here. This is what BSC means. Let's have a look. Do I have the ICME package index? Maybe I already have the specification. Oh, ISME, no. ISME Y 14.5 M. Oh, dimensions and tolerancing. Something like ooh. Does it give some tolerances? it tells you how to read everything. Yeah, sometimes I just don't know how to read things, and actually this could be useful. Coding a frame. I have to read this. I don't know how to do CAD drawings, 2D CAD drawings really well, so I know how to decipher the most basic thing, but there are lots of things I don't know. MABC, no idea what it means. I did not learn it in school. So, I didn't learn any electronics in school. What does BSC mean? And what is the tolerance? BSC. Okay, BSC is not described at all. I still have to read this document. So this is how you decode the values, but it doesn't mean what the values are. And I would really expect to put the tolerance. Here is their node 3 and 4. 3. Dimension D does not include both flange protrusion. Shall not exceed 10 per side. 0, 10, but this is not what this comes from. So we see that E1, this is the nominal value, and he added, he removed 7 or added 6 micron. Where does he get this value? Oh, he removed 6 or added 6. Exactly. Where does this tolerance come from? Because here it says 10. The protrusion here 6 gate burst protrusion, but this is maybe he didn't do it correctly. Dimension D, it's 6 the gate burst, 6 per end. But when dimension E1, which is the one we want, this is 10. It is not 6, so I think he made a mistake here when we create the package. This is 130. It was 137, right? Yeah, because E1 is 10, not 6. So we'll fix that. This is E1. Sorry. Is it E1? Yeah, body width E1. We need to values from here. E1. Here E1, actually it is written here E1. We don't even need the BSC thing. E1 is 0.291 to 0.299. Lead width. Let's look. I think the lead width should be something like, where are the leads? Here, L. Either L or L1. I think it's L, because L1 will be calculated somewhere else, and we will see L, 0.16 to 0.50. Okay, that's the lead length. Sorry, lead width. Lead width B. Is it right? B, 0.08 to 0.012. Okay, that's B. B. And in R, is it also called B? That's the pitch. A is the pitch. B. Yeah, it's also called B. It says 0.07, but we have to pick it from here. 0.08 to 0.0135. Oh, they want to be precise. Lead length. This is the L. Thank you. And this is the L. Lead length L 0.16 to 0.05. Yes. Is it called L for us too? L, yeah, it is 020 to 040. 020 to 014. Lead span. Lead span is, as far as I remember, lead span is E. Let's check. Lead span. Lead span E. Does it correspond? E 0 dot. Yes, it is. Here it is wrong. I don't want to really fix because it's not a major issue. The one on the back, it's so small parts, and plus tolerances, this doesn't make too much of a difference. But from the one I'm creating, I want it to be correct. This is also E. E 0 3 9 5 2 0.120. The pitch is called E, small e. I'll verify if this is correct. Here, this is also E, you see E divided by 2, E 0.25 PSC. Yeah, on the pitch I didn't add tolerances. I think it's okay. The pitch, E, things like that, tolerances are not too important. It's the same. Now, the height for all A, we only have 8, we don't have B, we'll fix afterwards. The height is, it's A, I think. I'm not, yes, it is A. And we'll check it. A, he says, yeah, we did check it, it's this. And in our case, it is also A, and A, is it the same? Yeah, it's the same for all. But we have tolerances on the height. 0.110. We don't have a height for B. Now, the body length, I think this is depending on, this is D, isn't it? Lead count, exactly. This is, body length seems to D. Oh, what is, this D is quite weird. I don't know what this D means. For example, here, I don't know what ABD means. I don't know how to read this, the thing, this thing. I could read the ISM thing which downloaded, but for now this is the value D, and the value D is fixed. It can't be fixed. This is the dimension D. See variations, you see? Yeah, D. This is what changes all the time. Body length, this will be D, and let's do it. For AA we have a body length of 0.620 to 0.630. Lead count 48. Normally this is also an, exactly, this is called N. Now we delete all the parts here. We have 4 variations, A, 3, 4. Let's do with AB. AB at 0.720 to 0.730, and we have 56 packages. For AC we have and then I have to tell which cable I'm using if I want to generate the parts and so on, and I want to compile it myself, blah blah blah. But this is for afterwards. So AC 0.370, 0.380, and the pin count is 28, and AD 0. This is okay, it's because it's 64 pins. 0.64 K20 to 0.860. This is this in millimeters? It can't be in a millimeter. The body length cannot be less than 1 millimeter. Ah, unit inches. So JDEC is probably something from the US. 64. Mentions pitch body. So yeah, everything is, you see that everything is, all dimensions are in inches, and we see that all dimensions are in inches here also. But I think so we will do this package. So this is package done. And you see, now we have an outline which everyone can use as template once we pushed it. For now we have it locally, and once I've kind of finished my project, once I've solved it once and I've ensured that it is correct, then I will push it to the repo, to mainstream. For now I'll have it locally. We want to share outline NXP, and for NXP it is called, let's see how they call CP, not CD. Okay, they don't put the minus afterwards, but this includes a minus, so I want to include the minus. This will be SOT 3701. And I'm sure here all dimensions are in millimeters. Yeah. And here it's only, this one is only for 48 leads. That's, yeah. So I want to find out how they do just for one package. Let's say the SOT. Okay. They don't do groups, they just specify everything. Makes sense. And I think, yeah, per default, per default, if you don't say anything, it is in millimeters. Unit millimeters. So body width, it's this time, see, it's different between people. So in this time it is not E1, the body width is E. Pattern sub, yes, it is a sub. E is 0.74 to 0.74.76. This is E. Lead width, this is what we called B, and what is called BP here. This part, is it BP? Here, for example, they didn't provide it in the datasheet, but they provided here, they recommend, this is the footprint for, this is the recommended footprint. And here they already put the dimensions, and you can actually use the recommended footprint. And there are other generators for footprints, which is the one, there's a big one which does that all the time. I don't remember the name. But yeah, they tell you. You can also say, what you can do is you can specify it even in CADA. You can specify and say, this is the footprint, generic footprint it uses, and then just below it, you can write your own footprint, and you can say in the specification, in the configuration, I want either to use the recommendation from the manufacturer, so within the part description, or I want to use a template. So in our case, we will continue with BP. I think we said BP. Yeah, BP. BP is the lead width, and it is 0.2 to 0.63. Lead length, it is called LP, and it is LP 0.6 to 1.0. I think I made a mistake somewhere. I'll have to check the part afterwards. Lead span. This is the complete HE. This is from lead to lead. H, and I have my capital E. Lead span is HE 10.1 to 10.4. The pitch is called, originally it's called E. Yeah, it's also called E. 0.365. And we only have one height. And the lead counts, so the height is called A, same thing. 2.8, that's the maximum. And they didn't put any minimum, so we will put 2.8. We have the body length. This is called D, also here. 16 to, no, 15.75 to 16. Lead count is N, do they say? I think they don't say which parameter it is because it is only one for all of them. And this way we created the footprint for this part. Everything in millimeter. I want to check the previous part. I think I made a mistake. No, I didn't. Okay, it's good. So now we have the status. We have two new things. How does it work? I think it's npm build. I never remember because we want to use this one now, which has the right footprint. npm build. Oh, maybe it's just install, and if you don't use sudo, it doesn't install it locally. Now it has to compile everything and check if everything is correct. Added, what does it? I don't know, okay. And now, and in bin, is it? Yeah, we have Kida. And now I have to tell in my script that I want to use this one, else it will not work. So yeah, this is job done. Close, 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 close. Single fork. We will not push it from now. We will push it once it works, because I don't want to edit it 20 times. We can close this, and yeah. Back to our parts. Up. This is the microcontroller. We don't care about this one. This is the analog multiplexer. This is the level shifter. Now we have the choice. Either we use the JDEC or we use the NXP. Because it's an NXP part, let's use the NXP one. This way we don't have to add the variation and find out what the variation is. NXP, and this is the number. Oh, but it's only for one of them. This is the SSOP. We also have the TSOP version. And it's again, is it there? At this time it is here. The MO153, this is already there, so we don't have to create it. But there is no outline for the other outline. The SOT outline is not created. The NXP SOT outline, NXP SOT, no, it's not. There's only the SOT one. But so we'll have a mix. DDG, that's 153, and the variation we have to find out by looking at the specification. Do I have MO153? No, 152 I do, 153 I don't. JDEC standards M0153. Let me, too many results, there should be only one result. M0153. Yes, download. Oh, G revision. Let's see, January 2018. Maybe we can even select within the document. No, we can't. Ah, we can sometimes, but not always. So we have 48 pins. Which variation is with 48 pins? 48, that's variation CD. Oh, there's another variation. FB. Too many variations. Which one is it? And there's another, yet another one. There's also JD. And BE. And probably an A variation and E. So, wow. A lot of variations. Do we have to find out the variation, or do we just create the footprint because it is faster and we just copy it? We have to download the datasheet either case. Oh, we can have a look here at the specification of this in this datasheet to find out the variation. But I don't want to. Let's download this. It is really fast. NXP. No variations. Plenty of things here. So we will use this and we will just create the footprint. We will not use the JDEC thing. So let's do that. You can go back here. So I will not use this one. I'm interested to see if he added data project IOVoodoo. How it's called? How is it called? Killer. Vim share outline JDEC. I'm just curious to see how he did it. M0153. If he added really all. Yes, he did. He added all the variations. Good luck. CP share outline NXP. We just copy the one we created because a lot of things will apply. 362 minus 1. It's a sub package, yes. The body width is, I think it's probably all the time E. Very often, so you see that across organization, what the acronym or what letter for the body width is different. Within an organization, it is very, very often the same thing. Don't rely on it, but still expect it. In this case, it is the same. E, it is 6.0 to 6.2. Lead with, it's probably the same. BP, is it the same? BP, BB? No, it's not. It is a bit smaller. 0.17 to 0.28. LP, the leads, length. Is it still LP? Yes, it is still LP. 0.4.0.8. It is smaller. It is a smaller package. Maybe we'll use this to save a bit of space, although we only need 2 of them. We will use the cheapest one. Lead span. That's HE, still HE, 8.0. Yes, it is 2 millimeters smaller. 8.3 to 9. 7.9 to 8.3. The pitch is 0.5. Okay, this is now a metric pitch. The other part is in period based. The height is still A. A is 1.2. Oh, it is less than 2 times thinner. It is very thin. Body length, it's still D, and I'm sure this is also different. Yes, body length is different. 2.12. Where's the body length? E 12.4 to 12.6. Lead count 48. And now we have the second footprint. This is how we've added 3 templates for parts. NXP and this sucked. Now we have created this part. We can add it to our repository, and we can add it to our parts list. Which one will we buy? It depends on the price. Just go here. It will be this one. Which one is in stock? DGG, that's the small one. And we have the, I don't know what 11 means. And there is also the L. Is this data sheet not up to date? The L isn't listed in the ordering information. Ordering information is the L. Okay, it is. The L is sub. And surprisingly, the L is more expensive. The larger package is more expensive, although I thought it was always less expensive. We will use the DGG version because it is less expensive. Are there more? Ooh, there are plenty of things, but DDG again. This is even more expensive. I don't know what the R means in the end. The LGR. The least expensive one is DGG, so we will use this one. And I think I will have to change it. Rake. No, I'll not get a rake file. Did I create a make file? Nah. Hardware. KEDA is in bin. This is where our version to KEDA is. Now, so this is my make script to generate from the footprints all the things. I do it from time to time. I think it's KEDA add, but I don't remember how exactly it works. Sorry. KEDA remote upstream. No, I don't have it anymore. Add. I think it knows that it is in library. Library. I see level shifter, and then I have to specify the package, which is TSSOP. I think it works this way. Okay. No such file directory. It knows that it is in library, so I don't have to put library this way. Okay, and now I have it to my list of parts. And if we look at my list of parts, I think it is here. Here you see nominal. This is the density level I'm using. Here you could specify that you want maximum and least. I use nominal. Prefer manufacturer? No, I don't prefer the manufacturer. I prefer the one which is generated based on the package. So the footprint will be generated on the package. Smooth corner means that the pin 1 will have round corners. And one additional way to have round corners. All other pins will have sharp square corners. And we have two parts. We have this one, LQFP package, and this one, a T-sub package. One part's done, and it only took us 1 hour, something like that. And there is still another part we need to do. It is the shift register. And I'm sure it also comes in at least 2 packages. We can move this here. This is the package. Data sheets. Yep. That's also an idea. Even more than 2 packages. 1, 2, 3, 4. Takes forever, but needs to be done. Okay, let's do it. How about it? Library, I see. Well, this is a shift register. Shift register. And XP. So what is the difference between HC and HCT? Because I need to name it either the one or the other. Then we look what the difference here. There's no difference in the package. I think it would at least be written in the HCT package what the characteristic is. They have the same characteristics. There is no difference between here. I think this is for HCT. The propagation delay is a bit different. Yeah, I think it has a different propagation delay. TPD. So here, yeah, this is where you see the difference. In HC, the propagation delay is at 25 is 52 nanoseconds, and the HCT it is 25 nanoseconds. The HCT is a bit faster, has better characteristics. Oh, and HC, I think it has the operating voltage is different. I don't know. Or HCT. Let's HCT. Oh, plenty of HCT. Here, inputs level. Here we see the input level CMOS for HC and TTL for HCT. The input levels. I think we require, we don't care for both of them, input level. Okay, that's the difference. And we can also put an alias actually on our thing. This is not, so this is important for ordering probably, and we will have a look at if it's important for us. Static characteristics, the input left. Why doesn't it make a difference here? I thought the logic level, the CMOS level are what is important, but it here. So it is. Here, this is the HC. We see that the level for high is 1.2 volts. This is for CMOS, and for TTL, it's 1.6. It is higher. So we don't care if we use the one or the other, because we will be at 3.3 volts. But CMOS is lower than transistor level, than TTL level. We'll just buy the cheapest one, or actually the one which is for 4 cents. But we'll call it HC. 74 HC because I think most of people call it HC. I don't know actually what most of people do. YAML. We don't need this anymore. We already have a template. We just need this template again. And I think we can also add an alias because it's the same thing. Oh, how do we add aliases? I think it's just alias. Let's see. Library, MCU. I know I've added an alias to the STM32 because here alias. Because the B and C is just a difference in the flash size. This is why I've added an alias. And the suffix is after the T. It's always different, but in our case, we just put an alias. Now, this is already alias. It's either HC or HCT. In our case, it's not important. There are plenty of variations. There are let's see, one, no. Ordering. We have SO, SSOP, TSSOP, and QFN even. SO, TSSOP, DH, VQ, FN. Description, I'll just copy paste from the data sheets. 3 state, why? Because the output can be put in high impedance mode. Such as data sheets, we will have a link to the data sheet. Not from TI, we're using the one from NXP. Are we buying from the one from NXP? We will need to check. So we will make the footprint from NXP based on the NXP data sheet, but we will not buy it from NXP because we found our source was cheaper. For example, NXP 70 cents. No, that's the shift register. Sorry, that's the level shifter. For this part, HC, or maybe the HCT is even cheaper, but here, for example, there are plenty of copies. Let's see if HCT is even cheaper. So here we find it for 3 cents even, and there are plenty of them available. HCT, is it even less expensive? Transistor to transistor level, they are less parts, I think, and they are more expensive. Yeah, transistor is more expensive than CMOS, and they are less stock. So we will have the non-transistor, we will have the CMOS level, which is good. CMOS level. For example, Texas Instruments, we see that it's 50 cents, and we've seen that one of them is 3 cents. But we have to check if this one has the same footprint, because we are making the one from NXP, because the data sheet is easier to read than this one, I'm sure, but we'll have to check afterwards, one thing after another. Oh yeah, the data sheet. We want the one from NXP, it's this one. Copy link address. Shift register. Eight bits. This is serial in parallel out is written in the description. I don't need to add it in the shift register in the keywords. I never use keywords though. I don't know why I put them. Maybe just to give an indication of on what it is. Pinouts. We have are the pins? Q, we have Q0, which is pin 15. Q1 is pin 1. Q2 is pin 2. Q3 pin 3. Q4 pin 4. Q5 pin 5. Q6 pin 6. Why Q7 is on pin 15, I don't know. There must be a reason, maybe from the package layout, but we're not checking now. Q7 is on pin 7. Q7S is a different one, yeah. It's Q7S is the serial output. Q7S is on pin 9. Master reset, which is output low, is on pin 10. We'll have to say this is inverting. 8HCP, I think this is the clock, isn't it? That's on pin 11. That's TCP, I think this is the data. Clock input, storage shift. Ah no, this is the clock for the storage. For not the shift register, but the storage register. 12. Output enable is on 13. Enable is also negated. DS, that's the data input, serial data input. Yeah, exactly. 14. Q0. There are two Q0s. 15. Oh, it's written 2 times in the data sheet. I have no idea why. VCC is on 16 and ground is on 8. Now we have to define the properties, right? Properties. Bidirectional, nothing is bidirectional in here. But let's just copy. Bidirectional, no, everything, no, they are outputs. MR, HACP, at ST, CP, I don't know what it stands for. Output enable, oh, this is here. And DS, these are output ground, inverted. We have master resets and output enable. These are both which are inverted. And we have outputs. Q and Q7S. This is if you want to change them. These are both outputs. After that, we have to define the schematic. It's an IC. On the left, we have all the inputs, and we will use the diagram, which they have some kind of logic diagram. We will. Oh, the logic symbol is also nice, but I'm more referring to logic diagram. So on the logic diagram, we will have DS as HCP, MR, HTCP, and output enable. On the right, we will have all the inputs and the serial outputs. Q and Q7S, on top VCC and on bottom ground, like always. Did we miss one? No, we didn't. Now we can specify all the packages. This we can close. It's one tab less in our editor. And none of the packages are created, I think, and we have to create all of them. Let's create them. Packages. Pin description. Where are the packages here? Packages. Yes, we have to create for all of them. But yeah, if we don't do the JSEG, it's pretty fast because we don't have any variations. What is good? This is good. Let's start it. I'll just copy one example. The one is SO. It will be SO16, but that's SO. The suffix. Yeah, we can add the suffixes. Ordering. We have D. It's the same for all of them. D is for SO. Then we have for SSOP. SSOP, we have the DB suffix. SSOP, we have the PV suffix, and DHVQFN. DHVQFN, the package is BQ. Suffix is BQ. We have to fix all the packages, but we have to create them first. Let's again copy and edit them. They are all no. There's one which is not sub. There's one which is Q something, QFN. And I'm a bit afraid to work on it. That's hard. That's okay. We'll find out how QFN works. At least we'll see something different. I don't know why they add one all the time. Do I have to remove one? Because it seems it's only one. Is there somewhere where there's something different than one? I'll check it with not the SOD, with the SOD YAML. He didn't add one. SOD 128. Let's see. XP SOD 128. I'm sure the specification comes with a 1 afterwards. No, it doesn't. Oh, patch not found. Come on. Maybe this helps. Yes, it's not -1. So we have to add the -1. It probably means something. Even if I don't know what it means, it probably means something. This is the first one. It's a sub package. So, oh, there's even a summary for all the things we need, but I still prefer this. Oh, they have added in millimeter and inches, probably because it is an inch. Yes, it is inch based. So this is probably why they added inch, because here we can see from here that this is inch based because of the pitch. We still want to edit in millimeter. So body width 3.8 to 4.0. 0.36 to 0.49. 0.4. The margin is really high here. 0.4 to 1.0. Sloppy process. LP, right? Yeah, yeah. Lead span HE 5.8 to 6.2. Pitch 0. The pitch is really high. 0.17. No, 2.7. See, sometimes I make mistake, and I will probably mean, but I have ways to verify it afterwards. You print it and you verify if it fits. Heights 1.5, 1.75. Body length D 0. Pin count it's 16. One package done. It's fast now. Now that we know how it works and I've explained everything, it is pretty fast. This is done. So this is for the SO package. Oop, and XP. This is the package. Duck. To drink. Not allowed to drink anymore. Okay. Next package. This one. SSOP 16. No, it. Yep. I want to keep you there. Don't use too much of my living space. 338 minus 1. Actually, what we can also do is, I don't know if this works, if in the template you can say use the housing from JDEC. That could work. I don't know. And for now, they are made, so I don't care. We use the specification. So, and here we see we don't have the units in inches because this is not an imperially based width, although it is 6.5 normally is, isn't it? I don't know. Body width. So E 5.2, 5.4, BP 0.25, 0.38. Lead length LP 0.631.03. Lead span HE 7.6, 7.9. Pitch 0.65. 0.635 would be imperial based. 0.65 isn't. Heights. This is A. This is 2.0. Body length. D. Still D. Yep. 6.0, 6.4. Pin count 16. One package done. Oh, and it is -1. This is a mistake. -1. That's done. So in this part, this is the SSOP one. Up. These up. this package up, up for 03 minus 1. Recommended footprints. Oh. Solder mask open. Also, exactly. Very often what you do on, so this is a different. What you do is whenever you have a footprint, sometimes within the footprint, the solder mask opening is also defined. Here, for example, they say pads, IO pad solder area. This should be the solder mask opening. This should be the solder stencil. This is something where sometimes it is defined in the footprint or land pattern, sometimes it is defined in the board. It's a setting of the board. And yeah, if you don't know the footprint, you don't really know, is it defined in here or not? It depends on the software you're using. I think in my case, it is defined in the footprint. And this, is it? I don't remember. We'll have to check. We can check afterwards. Let's do this first. So, body width. That's E as 4.3. Oh, this is a lot smaller. BP. 0.19, 0.30. LP 0.75. 0.50, 0.75. HE 6.2. 6.2. 6.6. Pitch 0.65, same pitch as the SSOP, it's just thinner. Height 1.1, a lot thinner. And body length D is 4.9, 5.1, pin count 16. Done. Yep, it's for this one. Last one, QFN, Peñas. QFN, do I have a specification for QFN? I think they don't know if they call it QFP or QFN actually. In the outline there should be at least one QFN. There is one QFP. Oh, there's also one. What is the difference between QFN and QFP? QFP is with pins. QFN is without pins. The leads. I think QFP is with leads. QFN is without leads. I'm getting tired. I'll open this one because this is with QFN, so we have an idea on. Copy this one. Copy, and it will be, the name is SUT 763 minus 1. Up pattern. Yeah, units millimeter. Is it unit or units? Is now something. We don't have to specify it because, but I like to specify it just so you know. By default, it is millimeter. And now we have to define everything. And there is a thermal pad. This is why I wanted to use the template, because I'm sure the thermal pad is specified within the template. Actually, it is maybe defined MOD MO241 outline JTAG MO241. No, it's not there. This is not specified. One thing after another. Lead height. QFN has lead heights. Ah, yes, it does. I think it's C. 0.2. Yes, that's correct. Height. What is the height? I think it's A. This is 1. This is max. A. Next, body width. And I'm sure there are a body width and a body length or something like that, because it is not square. So the body width is E. E is 2.4, 2.4, 2.6. We can have a look at the thing we copied. Body width, body width, body width, body width, body length. Okay. Body length is D. Body length. This is D and D. Oh, it's that. No, it's not. 4, 3.6. D. What else is important? The pitch. Yes, it is. But there are two pitches, aren't there? No, it's the same. Luckily, it's the same. Pitch is E. And that's a 1.0. Pitch is E. E is 0.5. 0.5. Lead width. That's, where is it? L. L. No, is it lead length or lead width? There are two things. There is a B. I think this is the B. B. This is the lead width. 18 to 0.3. 18.03. Okay, this is lead width. Lead length, exactly. This is L. And L is 0.3 to 0.5. Oh, what is pullback? Ah, if it's inside, we don't have any pullback. Is it specified somewhere what the pullback is? We don't have any though. Row count. Column count. Okay, I have to look at what I've copied from 200 to 20. Do I have it? No, I need to download it. MO220. Okay. A lot more complicated. I think the pullback is L1. This is what they call pullback. Body width, body terminal pitch. Ah, here they have names. Okay, this is something good. It will help us understand what things are. Okay, L1 doesn't say. Apparently there is no pullback. Right, L1 is pullback. Yeah. So let's edit the footprint again. What is column count and row count? For example, on GEB, I have plenty of variations. Lead count, okay. GEB, let's find something with GEB. Here, they have 8 pins. Row count 1. So one here on row, I think it's row count. We have row count 2. Because we have 2 pins on rows, and then we have I'm looking it upside. How is it correct to that E is the width or that's row count? Okay, it's better to see it this way. So I need to change that. The body width should be D. Let's make the body width D. And the body length E. So we see how we look at it, it's not upside down. So rows, we have 2 rows. Row count 2, these are these ones. And the columns, we have 6. 6 times 2, 12, plus 2 times 2, 4, and it makes 16. I think this is how it is meant. We will see, for example, for 16, we need EEC or EEE or EED, something like that. Pull back 0. Okay, lead length, I have it. Let's find for EE. JKL. Yeah, EE. Or EE is square. We need something which is not square. EE dot, okay. EET. EEC. LL. Wow, there's so many packages. The one who implemented that, poof. 3.3. Okay. It is not square. Is there something where it is, where the number of pins here, for example, where there are 3 pins on the side and 2 pins on top? I want an example of this. How is this called? So this is the pitch, this is the lead count, but it doesn't tell me how it is organized. Oh, there's so many tables. ND and E. I think this is the number of pins exactly. 20, 16, 6, 6 is 12, 8, yes, ND and E. That's the thing. ND, so we want something with ND and E different and 16 pins. Something like this, which is VHGB. Or VGHB, it's almost the same. VGHD, let's look for VGHD. VGHD, come on. VGHV, GHC, V. I'm sure we cannot. No, not searchable. VGG, VGHD, yeah, VGHD, VGH, GHD, VGHD, 6 times 8, ND, 6, NE8, ND6. ND is the column count. Let's see in this picture. Yeah, ND is the columns. These are the columns you see, D and E. So ND is on this side and E is on this side. And so ND is column count at 6. Yes, so it is the thing I know. I kind of think it is. Is there something else which is important? I think we have everything. Lead length, column, pullback, lead length. We have lead length, right? Column count. Lead length we have. It seems to be something like this. We can actually generate it and see if it looks okay. But this seems to be done. So it's this thing. BQ salt, and we will add the parts. We will add the part with Q, this suffix. We will see what it does. Add, exactly. Library, I see shift register. Adds this package, so this way we can export it and see how it looks like. Yep. He read it, and normally if I make rake library, it generates the footprints. Yes, it does. And the footprints are named after the IPC. The IPC has a naming list and a naming guide, and you, for example, see QFN. Here, so PQFN, I don't know why P. I think maybe of the height. 50p. What does 50 stand for? Probably the size. I don't remember which size. Oh, we don't need this one anymore. What stands for phi? That's the pitch. 0.5. That's the pitch. That's the size of the package. That's the number of leads. 16. Oh, the number of pins. And that's the density level. And this way it created the footprint. We can have a look at the footprints and look if it's correct. PCB, RND, Coral EDA. So this is my board layout editor. I'll speak about it once I'm using it. Now it's just to check subc, and we want to check this PQFN. Does it look okay? Yes, it does. See, 2 pins. This is just a marking. 1, 2, 3, 4, 5, 6. It looks fine. I could measure it. I think this is how the mark. So this mark is added. From here to here we have in millimeters. We have 1.8. Oh no, yeah, 3.62. Is it approximately 3.62 D? Yeah, 3.6. Works. And here we see pin 1. Pin 1 is this one actually. We go this way around, but it is marked. Yeah, for example, here, pin 1. This is not pin 1, this is pin 1. Not too important though, because I'm sure the marking on the package is where's the marking on the package? The top marking for this QFP terminal area index, terminal 1 index area. Terminal 1 index area, okay, so it means that it is, I don't know in QFN how you look at the package from the bottom, from the top. It could be nice to have a look at. Here there's no pin 1 marking directly. Oh, the pad. Oh, I didn't add the pad in the middle. I think the footprint also didn't add the pad in the middle. Did it? Here the pad is missing. Do we have a pad? Yes, we do have a pad. This is EH and EH. It's kind of nice to have it centered and to have the ground connection. It depends on the ground connection, but to have thermal dissipation at least. And the pad is not inside here. There is a way to add the pad. I have to look for it again. But for now, I wanted to see how does it know the pinout. Let's look for the part on DigiKey. It's this part. Or Mauser, this part, and it ends with ordering information BQ. BQ. Oh, no pictures. I want to see the real picture. Images. I don't do a lot of QFNs. Okay, here there's a notch to indicate pin 1, but it seems that on top there's nothing to indicate if you're in the right area. Oh, here's a picture. Oh, here's a dot, but it doesn't tell you which one is pin 1. Actually, let's see. Yeah. Okay, there's a dot. And does the top marking tell you where the dot is? Pin 1, no it doesn't. It doesn't tell you how the top marking is done, so I have no idea from the top how you would figure out which one is pin 1. Also because pin 1 is on the side and on the bottom. Okay, you have an index mark for pin 1. So you can see it from the bottom. From the top, I don't know how you would guess which one is pin 1. How do you know if it's the right way around? I would expect that H, it's written that the top is top. I don't know. That QFN is not meant for people looking at it, but machines looking at it. So the pick and place machine looks at it from the bottom. So it's more important for the pick and place machine to find out the indents in the bottom, which you see here. It's kind of the notch in the thermal pad. We want to add the thermal pad in our thing. I know that the thermal pad can be added. I've added it in my footprints, and one of the footprints, CATS library, MCU, STM32F400s. It's somewhere in the bottom, housing in BGA. I have not in the BGA, in the QFN tab. This is how you add it. So let's edit the thing again. Share, and we will add the tab, and I hope it works this way. We'll check it. So the specification tab, tab width is DH, and DH is 182.215, and tab height is probably EH, exactly. EH, and this is 0.85 to 1.15. So let's generate it again. And let's, oops, boing. And let's have a look at the how it generated it. Did it? No, it didn't generate the tab. So I don't know how you generate in QFP the tab. Oh, it is? No, this is the marking. No, it didn't put the tab. Auto crop. I didn't add the tab. I don't know how you add the tab. And QFN things, is it not called tab? I have to look at the files which generates it. It's an exposed pad. So here, let's have a look at the source code. Source pattern default, let's say QFN. Pad, quad, okay, that's quad. Pattern elements, housing QFN. So let's have a look at quad. It's common, probably quad. Has tab. Tab width, tab length. I did add it. And tab length, didn't I? Tab width, tab length. Yes, there's even, I don't know how thing. I don't know why it didn't generate it. Yeah, if it has tab, then lead count plus plus. And then these are the column spans, row span, column span with head width has tab width, tab length. Yes, it has both. Okay, I have no idea. Let's remove the parts to be sure that it didn't make it. Let's generate the library just to be sure. It creates it. Huh? Oh, it created, sorry. You see, it created not 16 but 17 because it has a tab more. It has a central tab. This is why we didn't. I didn't see it. It did create it, and now we have the tab, which is actually all corners around it, not only pin 1. Rounded corners is for all. Round corners just makes it easier for the for pulling back the solder stencil, where you put the solder paste. If you have rounded corner and you lift it up, it makes less of a mess. It makes it easier to clean the solder stencil. This is why I use rounded corners. So yeah, the tabs do work, and they created it. It created it. It was just a wrong footprint. See how nice Keda is. So I really recommend it. Now we have all parts. This one is done. Let's close what we don't need. Don't need. But we don't want this one. del add, remove, how is it called? Reset. Can del exist? No, it doesn't exist. Well, if we can't remove it this way, we can remove it this way. Now, which one do we want to buy? We want to buy the least expensive one, which is still in stock, which seems to be this one. So we look at the data sheet, it says D at the end. We looked at the NXP one. If you have look at the ordering information, D is the SO one. It's really the largest. Can we? So I would like to sort all in stocks this way. Logic IC this way. All which are in stock. Apply. We have only 30 remaining. That we look at the price. The price, the least expensive one is this one. See, for example, this one ends with an A. I don't know what the A is. This is the least expensive one. Oh, one is a SOP, the other is a SOIC. Probably the same data sheet. Let's have a look. It will be smaller than how is it called? Then analog multiplexer, and it will be next to the analog multiplexer. Chinese. And the outputs are named differently, the inputs are named differently also. Okay, I only want to see the package information here. This is the D, and the D is SOP. So SOP stands for SOP for our SOP 16 or for SSOP 16. We'll see, because we go to the packages, we have a lead span of 6 and a body height of 10. So TD10, 10. This is SO6. This is our SO package. The SSOP has a height of 6 in small things. And if we look at this, the A, I don't know what the A stands for. Package D is still 10 millimeters max. Okay, here someone didn't do the job. The minimum is 9 millimeter and the maximum is 1 millimeter. There's a 0 missing. Good datasheet. I thought this is generated. This is not written by hand, this table. I thought the software would fill up the table. You just select the E and then it fills out this table. I didn't know that. I've never drawn this kind of. I didn't use any software to draw in this kind of package thing, but apparently this is done by hand. This is not done by the software. Or maybe some software do it, some don't. I don't know. This one doesn't. The one they use here, because this is clearly a mistake. This should be 10. So our package is the SO package. Largest, but probably good enough. This is shift register, and we want the SO package. Let's generate libraries again, and let's have a look at how it looks like. Like library. This is 16. Yes, 16. PCB RNG. Coral EDA, sub-circuits, and this part. And this part looks nice. I don't know why it adds. This is just silk screen. This is to show the package. So, for example, on our package, we have here the silk in green. This is the silk screen for the top assembly. This tells us this is where you put the package. The corner is in here. Then we have in brown. This is the courtyard. The courtyard tells don't place any component within here, because the pick and place machine could make any errors there. This is the code yet. For example, this is information you don't always have in the footprint. I have it. And then in the seal screen, this is the black. This will be what's in the pad, and it indicates here the seal screen is removed from the pads with a kind of distance, so it doesn't interfere with the solder mask, with the exposed copper, and it still indicates you where the package will be. And in black is the size of the package. And then, so you have the lines, and added to it, we have 2 pin 1 indication. The dot, which is on top, on the side. On top, it takes a bit less space. Don't really care, you figure it out. And then we have here the extended line mark. This is the next pin 1 marking. We have 2 of them. And pin 1 is important also, so you could have this dot under the package right here. The problem is that whenever you place the component, the package of the component will hide this dot. So for prefabrication verification, you will have issues because the dot has disappeared. Here we have a dot and a line, which are outside of the package, so they're still visible even if the package is placed. For sub devices, it's doable. For BGA, it's a bit harder, but for BGA, it's another class of fabrication. So 3.5 hours, and we added all the parts, and I will not start the schematic. I will do something else. So, because if I start the schematic, I have to explain what EDA software I'm using, and this takes a bit of time. But now you know that's how I manage my libraries. And we have almost all parts. So we have parts which are missing. The other parts are generic parts like LEDs, voltage regulators, fuses, connectors, and I have most of them. If not, I will make them off screen. You know how it works now. And you can create your own footprints. Just if you don't have information, you can have still. That's also good. So the documentation is not that good for QEDA, but look at the source code. At this point, it's free, so pay a bit of attention and invest yourself also in it. And now we have plenty of footprints we will submit once we did the layout. But we will use the cheap part, which is this one, 4 cents. 3 cents. 3 cents per shift wage, that's nothing. And yeah, I need to order the chips now. Exactly. Before all stocks are empty, I'll take care of ordering the microcontroller. Because even ST doesn't provide them, all distributors don't provide them, LCNC is too expensive. I'm sure I'll find less expensive on AliExpress, and I need to order them now because they take forever to arrive. So this we don't need anymore, this we don't need. Current task, create Python library. This is what we did today. The next task will be adding all the parts to our library and then starting the schematic. So the schematic capture. And we will do that in the next stream. I don't know when, but since there's no one to complain about on periodic schedule, I'm fine. So for that's it for this stream. See you next time for the IOVoodoo schematic capture.